Hey folks, thanks for joining me. My name is Bobby Gunning. I'm a geophysicist at CNRL, and today I'll be presenting my talk, Predicting Microseismic Event Density Using Surface Seismic Alone. So our setting, we're in a multi-stage hydrofrac completion in an unconventional reservoir in Western Canada, and our two objectives are to use machine learning to establish a predictive relationship between microseismic event density and surface seismic, and then to determine which of these surface seismic variables are most descriptive of microseismic density outcomes. And we have a 3D surface seismic that's coincident with a 3-well microseismic program that was acquired during hydraulic fracturing. And from the surface seismic, we have reflection amplitudes, AVO attributes, elastic properties, and velocity and amplitude and isotropy volumes. And before we talk about the machine learning, I'd like to review quickly some concepts from anisotropy because they will become important when we actually go through the machine learning workflow. So there's two symmetries of velocity anisotropy that we can measure quite easily with high quality wide azimuth far offset seismic data. The symmetry in particular is transverse isotropy, where you have an axis of symmetry. And we can measure VTI anisotropy, that stands for vertical transverse isotropy, that results from fine horizontal layering. And what it looks like is in an offset sorted CMP, at high offset, we see reflection travel times are much faster. That's because the velocity traveling horizontally is faster than the velocity traveling vertically. And if we rotate that symmetry axis to become horizontal, we've got HTI velocity anisotropy. That's horizontal transverse isotropy. And this can result from geomechanical conditions in the subsurface, from stress anisotropy, or aligned fractures. And what this looks like, if we sort our CMP by azimuth, we can look at the kinematics of a reflection and notice that there's a sinusoidal shape. That's because depending on which azimuth our arrival is coming from, there's a shorter or faster arrival depending on the azimuthal velocity. And in this project, we're going to focus on HTI velocity anisotropy, but that doesn't mean that VTI velocity anisotropy might also be predictive of microseismic event density. So here's a azimuth sorted offset gather from the field. On the right to the left, we go from very far to very near offset, and you can see there's different alternating colored columns which go from 0 to 360 degrees of azimuth. And I've pointed out two positions. The upper position is where we have sinusoidal reflection kinematics, which indicates that velocities are varying azimuthally. And in particular, this process, if we want to collect the information at VVAZ, stands for velocity variation with azimuth. But then I've also pointed out below that there's amplitude anisotropy. You see there's oscillating amplitudes depending on azimuth. That's AVAZ, amplitude variation with azimuth. And we can represent this velocity anisotropy with a vector field. So here's a sample from a handful of wells where we've got good velocity anisotropy measures in the subsurface. So the vectors represent the HTI seismic velocity anisotropy. The magnitude is the amount of anisotropy, and the direction is the azimuth of the fast velocity. And VVAZ requires very good signal-to-noise ratio, and then AVAZ, that requires exceptional signal-to-noise ratio. So you need to have near-perfect data to be able to resolve AVAZ. VVAZ is a little bit easier, but in general, you need very good data for both. So now that we've reviewed anisotropy, let's actually establish a predictive relationship between surface seismic and microseismic during completions. So this is a single wells microseismic event catalog where each circle is an individual microseismic event. And what we can do is bin this map with the same binning strategy that we use for the surface seismic and count how many microseismic events there are in each bin, which gives us this map. And you can see that there is some variance in the microseismicity during completions during this well. At the toe and at the heel of the well, there's less microseismicity than in the center of the well. And we'd like to answer the question, why is this the case? Is this something that we could have known beforehand? And can surface seismic be that predictive of that microseismic outcome? So now at each XY coordinate, each bin, we've got a microseismic event density, and then any map we'd like from our 3D seismic. So in the end, we'll end up with a table that has every single bin as a sample, and then as many seismic variables as we'd like. In the end, I ended up with 20 prediction variables, but I started with much more than that. And I'll explain how I actually got down to that 20 variable in a few slides. And then we'll also have a dependent variable. That's what we're going to try to predict. That's our microseismic event density at that particular bin. So in the end, we'll have 2,105 samples or bins and 20 prediction variables, which will give us 42,000 data points. So how I actually chose to remove certain variables was by using a multicollinearity cutoff. Multicollinearity refers to prediction variables that have high linear correlations. Linearly related variables are numerically indistinguishable from each other in machine learning algorithms, and if we want to be able to interpret the results of each of the individual variables in the ML model, we want to have linearly independent prediction variables. So we should remove multicollinear variables from our prediction. And for instance, in the zone of interest in this project, the elastic properties at a given level are multicollinear, and I've got this plot here that shows that VP, VS, and density, the points that I collect from that interval, align on a plane, plus or minus a little bit of noise. The fact that those points exist on a plane means they're going to be numerically indistinguishable in the end of the modeling. So what we should do is remove 2 out of these 3 variables and just put one of them in there since the information contained is identical in all 3. And so here's a seismic attribute correlation matrix. And you can see that at the intersection of different variables, I've got their Pearson linear correlations. And the criteria I used to reduce variables was I removed all variables or one of a pair of variables that have correlations greater than 0.7. And the criteria that I picked for keeping certain variables was manual. So for example, I've got 3 different intervals that I'm pulling seismic maps from. For the upper interval, I wanted to keep a certain elastic property, and then for the lower, I wanted to keep a different. So then I have a little bit of flexibility and choice of actually choosing which variables to remove. If there's one variable in particular that I'm curious about its impact on the microseismicity outcome, I'll remove that variable or keep it depending on what I'm interested in. So what are the prediction variables? So starting with velocity and isotropy, the percent anisotropy and azimuth. Elastic properties, so P impedance, shear impedance, and density for 3 individual intervals within the zone of interest. Reflection stack amplitude. The intercept and gradient 2-term AVO fit for the 3 intervals. And then amplitude and isotropy, so using the AVAZ, azimuth, and gradient. And then I also included a variable that was the distance from the bin to the well. So that's the shortest distance from each of the individual samples to the well that's being completed. And then a random number to act as placebo control. So how did I train the model? So I'm using the gradient boosted tree algorithm, which I'll talk a little bit about. But here's a flow chart of the actual total workflow. So starting with the input data, that large table, split it into a training data set and testing data set, and I'm using a 2/3, 1/3 split. Train the gradient boosted tree model, evaluate the performance of that model on the testing set, and then tune the hyperparameters and get an optimal individual model. Finalize it, and then use permutation importance, single variable analysis, and Shapley values to interpret the machine learning model in the end. How does each variable impact the result? So why gradient boosted trees? So gradient boosted trees, they can be used for regression or classification. It utilizes an ensemble of decision trees, same as a random forest would. But it applies boosting, which is a technique to exaggerate data that improves the tree from being a relatively weak predictor to a strong predictor. These models are very strong generalizers, and they're somewhat immune from overtraining. It doesn't require feature normalization since no explicit distance calculations are made in tree algorithms. It's efficient at handling outliers, and these models are extremely interpretable. So all of these reasons lead me to choose this particular model type for this project. And an example of a ensemble of trees might look like if we would like to know what are the attributes of the survival of passengers on the Titanic, we can take those individuals' attributes, create a decision tree, and then create an ensemble, and then interpret, well, what is the likelihood of a person under a certain age or over a certain age surviving on the Titanic? So I use 2/3 of the data set for training and then 1/3 for testing, and then 4,000 decision trees, each with 3 splits, and then apply 4,000 iterations of boosting. And you can see on the plot that as we increase our iterations of boosting, we reduce the error of both the training set in blue and the validation set in red. And what I'd like to see is that that validation set converges and remains flat. If it starts to increase, that means that we're overtraining. In this case, we're not overtraining, which is a good sign. And in the end, we can plot our true microseismic event density for every bin against the predicted microseismic event density at that bin and see how linear the relationship is. In a perfect prediction, will fall on the black line. And you can see that both the training data set in orange and testing data set in blue are quite close to that perfect line. In fact, we can say that there's roughly 20% prediction error for the blind test data. So what that means is that using only surface seismic data, we can predict before drilling and completions what the microseismic results are going to be within 20%. So that's quite good. That implies that surface seismic data is descriptive of what's happening during completions. So let's look at a map of the true event density and then the prediction of event density. And I'll flip back and forth. And in general, I think we can observe that the trends are well preserved. So at the toe and the heel, there's less microseismicity, and in the center, there's a little bit more. But there are a few areas where it's imperfect. And that's sort of where that 20% error is lying. But in general, the trends are preserved. Let's look at a different well. Same kind of story. True, predicted. And I'd like to point out that there's this region here near the toe that's not really as accurate as the rest of the well. And we can ask, well, why is this region not as accurate? Was our completion inefficient? Should we have expected more microseismicity here? Are we missing stimulated rock volume because of the fact that something happened with completions? Or is our seismic actually not as predictive as we think, and there's other things that we need to consider when we're improving our prediction of microseismic? So could we include well geometry attributes or completion design to improve this model? I think absolutely, yes. We could add more for sure to improve the model. So those examples were for both training and testing sets. So just to do a blind check, this is for the testing set only. So this is the true event density for the testing set, and then the prediction. And I'd say same interpretation. In general, trends are very well preserved, and we have a strongly linear prediction versus true event density, which implies that using only surface seismic, we have a good prediction of what microseismic outcome we should expect. So now that we've built a model, we can apply this elsewhere in the field. So suppose there's a new drilling program that we've got 6 planned wells, and we can only drill 3. So in this case, we could easily rank these wells by stimulated rock volume expectations before drilling. I think we'd probably start with the upper 3 wells. So now we can do this field-wide and see what kind of microseismic should we expect in our new drilling programs. Also, we could add more microseismic programs to the model. So we only use 3 programs here. We could add many more to try to generalize even further. So which of these seismic features actually are descriptive of the event density? Now that we know the prediction's good, what is the most important variable? And so we can delineate that using a technique called permutation importance. And how it works is we choose one of the prediction variables. In the testing subset table, we just randomly shuffle that variable. So for example, if we take our shear impedance column, just randomly shuffle it. Predict the event density using that table where all else is equal except for one column is shuffled, and then evaluate the model performance. If we see a significant decrease in the model performance, then we know that variable is important in this prediction. And then we're going to repeat that process 500 times for every single variable and then compile the statistics. So what is the decrease in the explanation of the variance by having this variable shuffled? If it's decreasing the prediction a lot, then we've got a problem. And so we're going to order the variables by the average decrease in accuracy. So then the most important variables are going to rank the highest. And so in this case, at the top, we've got the distance to the well is the most important variable. Well, that makes sense. If you get farther from a well, you shouldn't expect more microseismicity, you should expect less. But interestingly, the second and third most important variables are the VVAZ velocity anisotropy, both the percent and the azimuth of the anisotropy. And then everything else is kind of more further down the hierarchy than that. In fact, the majority of the variance, 77% of the variance in this prediction is explained by only three variables: the distance to the well, the magnitude of velocity anisotropy, and the azimuth of velocity anisotropy. So we can kind of ignore everything else since, roughly 80% of the variance is explained by only these three surface seismic variables. So what is the actual impact of changes in these variables in the amount of microseismicity that we observe? So looking at distance, exactly what we'd expect. As you get farther from the well, there's less microseismic events. Looking at the velocity anisotropy azimuth, there's fewest events when the fast velocity is in roughly the direction of minimum horizontal stress. And that maps exactly to what we would expect from first principles. If we see that there is velocity anisotropy that's aligned, pointing in the direction of maximum stress, we'd expect more stress anisotropy in the subsurface and more microseismicity, since more stress anisotropy results in a larger Moore circle that's going to intersect its failure envelope more easily than when there's less stress anisotropy. And then looking at the actual percent anisotropy, more velocity anisotropy results in more events. So what we would like to see is that those vectors on our anisotropy map are larger. And so now that we've taken these slices through the model, let's return to the velocity anisotropy and microseismic event density map and see if we can qualitatively make the same observations. So looking at the toe and the heel of this particular well, the anisotropy vectors are actually pointing kind of less parallel to the maximum stress direction, which is in roughly 30 degrees from north, where the vectors point in the center of the well, where there's more microseismic event density. And what we can do is make a Rose diagram for this particular well, and each point on the Rose diagram has a position and a color. The position is the velocity anisotropy, the magnitude, which is going to be the distance from the center of the circle, and the direction, which is going to be where on the circle the point is. And then the color, that's the actual microseismic event density. And I think there's two key observations we can make on the Rose diagram. There's more yellow when we're in a certain azimuth that's aligned with maximum stress. And there's more anisotropy as you get farther away, or more microseismic event density as you get farther away from the center of the circle. So I think strategically, it makes sense, if you can, in your field, to do the velocity anisotropy analysis and try to drill wells that have better anisotropy conditions first. And if we'd like to interpret the entire model in one place, we can use a Shapley plot. And so how this plot works is, let's look at one row. So the first top row there, that's distance to well. The color, that's the actual value of the row, so the value of the distance to the well. So pink is long wells, blue is short wells. Pink is far distance from the well, and blue is close distance from the well. The position on the x-axis is the impact on the microseismic event density. So if we take the very far right side, that means that we have a positive impact on the model, more microseismic event density, in other words. So we can say that when we have a low distance to the well, we have more microseismic event density. And then we could apply the same interpretation for every single row and have a way to see how does each of these individual variables impact microseismic event density outcomes individually. And you can see that the diagram is sort of oriented where the widest row is at the top and the narrowest row is at the bottom. And what this sort of is doing is ranking the variables in terms of their importance. So it's an alternative way of creating a hierarchy of which variables are important. And the ranking is going to be very similar to the permutation importance that we did earlier. So to summarize, we created a model that predicted microseismic event density using surface seismic. We can explain very well microseismic event density in the subsurface using only surface seismic. And the overwhelming majority of predictive power from the surface seismic is coming from the velocity and isotropy. Thank you very much for listening, and I would love to take some questions now.